Thank you very much, Professor Vinayak ji, and I thank the organizers for the invitation to be part of this very momentous occasion marking the 80th milestone of a venerable friend and a mathematician, Professor Kulkarni. I had met him long back while I was visiting HRI, and he had recently joined as director over there. And I used to visit HRI quite frequently, almost every 2 years. So this association is about more than 15 years old now. And ever since we have been in touch on many occasions. I mean, I have learned quite a good deal from him. Of course, in mathematics at some places, but more importantly, in his vast repertoire of knowledge in Indian knowledge system, and has been prodding me to read a lot of stuff which I have been doing, and I hope that I'll be able to make a fairly good acquaintance with these things and then discuss these issues with him. And I also been sharing my stuff that I keep writing, not exactly on IKS, but on other issues which he then gets back, and a long series of emails and discussions follows. I have learned quite a good deal. Thank you very much, Professor Kulkarni. And well, I mean, I wish you many, many such milestones in the years ahead, very fruitful and eventful years ahead. So it has been a pleasure to have been associated with you all this while. So I'm going to talk about the topic that's already displayed on the screen, something called Lipschitz geometry of Banach space. Well, Lipschitz geometry is actually a generic concept which makes contact with many other disciplines. Well, uh, if you can read it, or I will read it aloud, at least parts of it. The idea is that on a Banach space, you have a norm, and that's about it. But then the norm has attached to it a metric, which you can define in an obvious way by writing dxy equals norm of x minus phi. And then you have further weaker structures arising from the matrix, which is the uniform structure. I mean, a Banach space comes across not only as a matrix space, but also as a uniform space, and by virtue of that, also as a topological space. So the question arises as to what extent can these weaker structures, the topological, the mere, general point set topological structure, or the uniform topological structure, or the matrix structure, without the linear structure being part of these weaker structures, to what extent do these capture the entire, uh, the structure of the Banach space as a linear space equipped with a norm? And this is really amazing that it's the metric space, the metric structure, which doesn't have any, linearity associated to it. That's already, deep enough to capture the linear structure, and in many significant ways. Uh, I mean, to cut this discussion short about what Lipschitz geometry is all about, it turns out, as an example, that if you are given two normed space, let's say real normed spaces, and if they are isometric, so there is a bijective isometry existing between these two spaces, which is not assumed to be linear, and then it's already an affine map, which means it almost captures the linear structure of the spaces. So if you assume this isometry to map zero to the zero element, then it's a linear isometry, by virtue of which you then identify the two given Banach spaces as completely, as complete photocopies of each other. So this is an old result of Mazur and Ulam. But then isometry is again strong enough. You don't assume that it's linear, but then suppose I have a bijective Lipschitz map. So I'm going to give the definitions in a little while. Suppose you have a Lipschitz map, which is bijective from a Banach space X to Y and has a Lipschitz inverse. The question is, does it happen that the properties of X are carried over to Y, some important properties, or the other way around? Again, it's surprising that a lot of structure gets captured in the process, linear structure. For example, if one space is a Hilbert space and you have a bijective Lipschitz map, or say a bijective uniformly continuous map with a uniformly continuous inverse, then the other space is also a Hilbert space. It's isomorphic with a Hilbert space, and it's quite a deep result, quite non-trivial due to per inflow. So the other surprising aspect of this point of view is that this Lipschitz geometry is part of a wider program, the so-called Ribe program, RABE. This was initiated in the early 70s, and it seeks to study a Banach space merely as a metric space. And the metric spaces, again, it turns out that they have such a deep and hidden structure that it's enough uh, to disregard the linear structure of a Banach space and look at it only as a metric space. And you get a lot of information about the Banach space in question. And it has, this point of view has also found applications in such diverse disciplines as harmonic analysis, geometric group theory, Riemannian geometry, probability theory, data structures, algorithms, and in many other areas. So quite a rich discipline, but then I'm concerned with its impact in Banach space theory. So I fix some notation, X and Y and Z will throughout Banach space, X star will be the dual of X. All bounded linear functions on X equipped with the sup norm, and then Bx will be the closed unit ball of X. So this is defined in this way. All those X's whose norm is less than equal to 1. Lxy are all bounded linear maps from X to Y with the sup norm again. And then these symbols, L and P, these are Rn's equipped with the P norm, where PL norms have been defined in this manner. And when you take P to be infinity, then you give it the sup norm, the max norm. And its infinite dimensional version would be L infinity, which is the Banach space of all bounded sequence of scalar complex. And then C naught, which sits inside L infinity as a closed subspace, consists of all null sequences, all those sequences which go to 0. So that's about it. And with this terminology, I think I should be able to proceed ahead. And then there's a classical notion of what's meant by a retraction that we come across in the first course on topology. So if you are given two sets, I'm sorry, this is A, B contained in A, so there should be an ambient space X. So you have two subsets A and B of X, and and then we say that you have a retraction from A to B. B is a smaller set than A if this map coincides with the identity on the smaller set. So this is a set theoretical notion to begin with, but then when the ambient space has some structure like if it's a topological space, then you talk of a continuous map, and in case it's a uniform space, you talk of uniformly continuous retractions. And in case of a metric space, you have Lipschitz retracts, so on and so forth, depending upon whether the given F is continuous uniform or Lipschitz. Okay, and the Lipschitz map is defined in this manner. So you control the distance between the images by a constant which is independent of X and Y, obviously. And when I take K to be 1, then I get what's called the notion of a non-expensive map, or some people call it traction. Now, again, a classical theorem of Brouwer, again, which we learn in our first course in algebraic topology, is that the unit sphere is not a continuous retract of the unit ball. Equivalently, every continuous self map on the unit ball has a fixed point. And well, I mean, there are several proofs appealing to homotopy theory, homology, degree theory, so on and so forth. But then there are also, proofs which make use of advanced calculus, like Stokes' theorem and all that. So those are very nice, beautiful proofs. That's a very nice proof, and I wish it could be covered in a first course on topology, I mean, or maybe in multivariable calculus. So now this happens, Brouwer's fixed point theorem. It's in Rn, right? Equipped with any norm. I mean, they're all equivalent, we know. And if you take the plane, then equipped with the Euclidean norm, then it turns out that the closed unit disk is a non-expansive retract of the unit sphere, the unit disk. So here you give it, you give it the Euclidean norm, and then you can choose your continuous map to be even a non-expansive map, in this sense, where you take K equal to 1. But then how about other closed convex sets in the Minkowski plane? Again, this is not straightforward. I mean, this is quite a difficult result, that if you take the plane and give it any norm, then the closed convex sets are non-expansive retracts. So there is symbol missing. So a closed convex set, in particular the closed unit disk, is is a non-expansive retract. And in higher dimensions, the situation is quite different. For example, if you have the three-dimensional space, and if you take the plane, making intercepts of 4 on the coordinate axis, then this plane does not arise as the non-expansive retract of R3 of three-dimensional space. The reason is that if you look at this distinguished point D, the point 111, you can easily see that this is at a distance of 1 from each of the points A, B, C, which lie on P, 220, 202, and 02. So these points lie on the plane, and then this point has a distance of exactly 1 from each of these points. Of course, I mean, I am giving R3 the maximum norm. So it's not the Euclidean norm. But then if you have a non-expansive retraction from the big space onto this plane, then what happens? It will move D to a point which would necessarily bear a distance strictly greater than 1, at least from one of the points A, B, and C. So this D has the property that it is at a distance of exactly 1 from each of these points. You take any other point, then it will be at a distance of strictly greater than 1 from at least one of the points. You are using the sup norm, as I said. Okay, so that's easy to see. I mean, we have to draw figures to convince ourselves that it's exactly that. And if you take Rn now equipped with the Euclidean norm, so Ln2 is Rn equipped with the Euclidean norm, then every closed convex set turns out to be a non-expansive retract, which means that if you have a finite dimensional space of any dimension, then closed convex sets are Lipschitz retracts. It follows from the previous statement, asked probably. It follows from the previous statement mentioned over there that closed convex subsets of Rn with the Euclidean norm are non-expansive retracts. The reason is that all the norms on a finite dimensional space are equivalent. So that introduces a certain constant which gives rise to Lipschitz. But the situation in the infinite dimensional setting is vastly different. So if you take the Hilbert space L2, let's say, all square summable sequence of scalars, then this map, if it's well defined from the unit sphere of L2 to itself, you can easily see that it doesn't have a fixed point. So here you see that the unit sphere is a continuous retract of L2. The same reasoning as we do in the finite dimensional setting. So no retraction theorem and the existence of fixed points for the unit ball in Rn are equivalent. And so here you see that the unit sphere is a retract, a continuous retract. And there's nothing sacred about the Hilbert space. In the general setting of Banach spaces, we have a result of Goebel and Kirk, saying that every infinite dimensional Banach space has this property.
Yeah.
So every infinite dimensional Banach space has the property that there are continuous maps defined on its unit ball, which are fixed point free. In other words, in each infinite dimensional Banach space, the unit sphere is a retract of the unit ball, unlike the finite dimensional space. So it, in a way, Brouwer's fixed point theorem characterizes finite dimensionality in Banach space. Okay, so just keep it in mind. I mean, this is going to lead to many more questions. I mean, it's not the end of the story. The question here is, for example, Goebel's theorem is whether you can choose these fixed point free maps to be better than continuous. Let's say uniformly continuous or Lipschitz. And that's far, far more difficult. And we will see a complete answer to this question in the slides that follow. Now, a small digression here. Let's forget about these fixed points and come down to proper Banach space stuff. You are given a Banach space and a subspace M of X. We say that it is linearly complemented, which is the linear version of a retraction. This subspace is linearly complemented in X if you can find a continuous linear projection from X to X, whose image is M. So retractions are, after all, idempotents. They are projections, P square equals P. If you can choose it to be linear, then there's a special name given to these subspaces, which are called complemented, linearly complemented, to be precise. And this can be shown to be equivalent to the statement that if you quotient out X by means of M, then the quotient map admits a continuous linear lifting, which means that you have a right inverse for this map phi from the quotient space to X, which when composed with phi gives us the identity map on the quotient space. So that's called a lifting. And these two statements are equivalent. Now, so here this is possible as long as M is a linearly complemented subspace Y, a subspace of X. Then you take the quotient map, it admits a continuous linear lifting. Suppose now I have a more general situation involving a pair of Banach spaces X and Y, and we have a surjective continuous linear map from X to Y, which is more or less equivalent to saying that Fx from X, a quotient of X, quotiented by the kernel of F. So it is the same. Now, once you have this kind of a situation, the question arises whether this F admits a continuous linear inverse. Now, in the previous case, as I said, if M is, nicely placed inside X as a complementary subspace, then the quotient map does admit a linear continuous inverse. Now here, we don't apparently have that kind of a situation. You do have a surjective continuous linear map from X to Y. whether it has a continuous linear inverse. Well, that doesn't always happen because it turns out that the kernel of F may not necessarily be complemented inside X. But then you can still choose a continuous linear right inverse of F, which is homogeneous, positively homogeneous. So which means F alpha X is alpha times F of X for alpha positive, non-negative. And you may not be able to choose it as a linear map always, unless the kernel of this map is complementary. And this is always so. You can choose a continuous map. So that's the first thing that we get. And then it's not really linear, but it captures the homogeneity part of a linear map. Now, again, this is going to lead to a whole lot of questions, which we are going to encounter. Just now, C0, as I said, null sequences are a closed subspace of L infinity, bounded sequences. Now, how are they placed inside that? It turns out that C0 is not complemented with L infinity. Complemented in the sense I have just described it. So which means that there's no continuous projection from L infinity to itself whose image is C0. So that doesn't happen, but it's always a Lipschitz retract. That's wonderful. I mean, that's something really great. C0 sits inside L infinity as a Lipschitz retract. And you can choose your K of the Lipschitz retraction to be 2. It's a 2 Lipschitz retraction. So therefore, C0 is a Lipschitz retract of L infinity. And how about the general case of Banach spaces? Well, if you have a closed convex subset of a Banach space, then it turns out to be a continuous retract of X, an absolute continuous retract of X. That means absolute continuous retract. So therefore, you can take any superspace containing A as a topological subspace. Then you have a continuous projection, retraction from the big space to this A. And this always happens. So every closed convex subspace of a Banach space is an absolute retract. It's more than a retract sitting inside X. Now that is, again, not straightforward. It follows from this well-known theorem of Michael, which makes appeal to some terminology. I think it's interesting enough not to miss out on. Let me briefly say what the theorem is all about. If you have a matrix space X, or say a Banach space X, the notion also makes sense in general matrix spaces. So let's fix a Banach space and look at all non-empty closed convex subsets. Closed and convex subsets of X, then you can give it a nice matrix structure defined by means of the so-called Hausdorff metric, which is defined in this. So what you do is you fix your A. You said you want to define the metric distance between A and B. So fix A and choose any X in B and take the minimum distance between X and A. So it's norm of X minus 5. Y belongs to A. And you do the similar, you do something similar with B and take the minimum distances and take all these distances and take their supremum. You can check that it's a metric on HX. Now, if you have a map from some metric space M to this metric space HX, it's a set valued map, assume that it is lower stubby continuous, so which is the multi-valued analog of ordinary continuity. So it doesn't pull back open sets to open sets. That doesn't make sense. Instead, what do? You take any open sets in the range space and look at all those X's in X, such that phi X intersected with that open set is non-empty. So in other words, if phi is a single valued map, then it is continuous exactly when it is lower semi-continuous. And Michael's theorem says that once you have a set valued map, which is lower semi-continuous, then it admits a selection. That means you have a map phi, this small phi from M to X, such that for each X in M, phi X can be chosen to be in this capital phi X. I mean, I should have used different symbols, but this is what it is. So you pick up some element in each phi X. So phi X is a subset of X. It's possible, Michael's theorem says that it's possible to select a certain element in the image of X under phi so that the resulting map is continuous. And it's quite a non-trivial result. It had appeared in the late 50s in the annals. And it has lots of applications, many applications and various generalizations. Okay, now keep this thing in mind. From this, I mean, we get, look at the last line. So from the previous line, from the previous statement, you can also derive that you have a continuous selector. So what you do, what does that mean? This means that we have another map from this HX to X itself, such that phi of A for each A in HX is an element in A itself. So that can be easily deduced. And further examples of Lipschitz retracts. Now, if you have a compact Hausdorff space K, and if you look at all bounded uniformly continuous functions on this set, now, then it turns out to be a 12 absolute Lipschitz retract. It's a Lipschitz retract with constant equal to 12, which was then improved to 2 by K by Colton. And from 12 to 2, it was quite a hectic task, quite a difficult task, which he was able to achieve around 2008 or thereabouts. And then look back at this HX, which I have defined here. The last slide. This also turns out to be an absolute Lipschitz retract with the constant equal to 8. And this is again one of the active areas of function analysis, to improve these constants, K. So like in the case of CUK, the bound was improved from 12 to 2, and nothing better has been done in case of HX, but I guess this is sharp, and I don't remember, I don't recall any references to that effect, but this is what it is at the moment. Now, Michael's theorem says in the last line that you can choose a selector from HX to X, which is continuous. So the question is whether you can choose a selector from HX to X, which is uniformly continuous or even Lipschitz. Well, it can be shown that if the space is finite dimensional, then you can always do it. And it was conjectured that it's true for all infinite dimensional spaces. Till 1971, it was settled in the negative by Pozuchelski, and independently much later by Brzezowski and David Yost in 1989. Of course, the methods are entirely different, but it looks like the last two authors were clueless about what Pozuchelski had done in 1971. So the results are the same. Techniques are different, but one wonders why there was such a long gap of 18 years during which the former authors didn't know about. Yost and Brzezowski didn't know what Pozuchelski had done in 71. But then they...
dimension is countable?
Pardon?
Dimension is countable for this negative, answers?
No. It is any Banach space. Finite, infinite dimensional. Infinite dimensional countable.
Separable or not?
No. Regardless of its dimension, of its separability.
Without separability, the problem becomes very kind of amorphous, in my opinion.
You mean?
No, I
what
mean
exactly?
that becomes more set theory.
Yeah, I mean, no, I mean, you see, the point is that even for separable Banach, infinite dimensional Banach spaces,
Yeah.
it's not straightforward. The result, the answer is again negative, and the effort is
So, where were these results published? Positelski and
Positelski was in a Russian journal. I don't recollect the name, and the second one was in Michigan Math Journal.
I see. So they did not come to know of each other's results.
Right. Yeah. So this is really fascinating stuff. I mean, one of the positive consequences of this gap between the two proofs suggested by these two sets of authors is that they came up with entirely different techniques. Otherwise, if they had known about the 1971 paper, perhaps try to give another.
Then the second method would not have appeared. Perhaps
would not have appeared and would not have been thought about.
Yes. So there are always advantages.
Exactly. Exactly. Yeah. So now let's come to the Hilbert Space case. Hilbert Space have a very nice, rich geometry, and unlike in the case of Banach spaces, closed convex sets are not merely Lipschitz retracts; they are contractive retracts. I mean, non-expansive retracts, non-expansive. And the retractions can be chosen to be what are called the metric projections defined in this fourth line. So it is the it's a set valued map in general for Banach space, but for Hilbert space, the set is a singleton, and it turns out that the resulting map is a non-expansive retraction. Okay, so that's what happens. And even converse is true. That was done by Ribe in 1977. The previous statement in the second line up there characterizes Hilbert spaces. So if you have a Banach space in which each closed convex set is a non-expansive retract, then the space is a Hilbert space, and isometrically at that. So there's a linear isometry between X and a Hilbert space, which results in the process. Now the question is, can you expect better, regularity properties of the retraction of Ribe's theorem? So in other words, can you choose it to be, Lipschitz? I mean, more general than a non-expansive retract. And we have a recent result in this direction last year by Peter Hajek. And this is remarkable, both in terms of the statement and the proof. He showed that given any Banach space, then compact convex. I mean, he assumes compactness in place of closed convexity. So if I have a compact convex subset of a Banach space, that it turns out better than a continuous retract. So uniformity. And how about Lipschitz retract? Of this compact convex? Well, that happens exactly if the space is Hilbert space. Actually, he had made this statement in theorem B. He had made this statement in his proof, in his paper, without giving a proof. And when I read that, I was trying to work out the proof, but was unable to think of a possible line of argument. Then I wrote to him, and he gave a proof which was quite mouthful. quite long and difficult. And when I asked him why didn't he choose to include it in the paper, he said, I thought it can be done easily, but then it's not that easy. So I now include it in my paper. So he has finally included it there. So it's not straightforward. So he has added about 1.5 pages more of this. Now,
what is situation in reflexive spaces?
pardon?
What is situation in reflexive spaces? Because which
In
sits
respect
somewhere
of
between.
which theorem?
Huh?
In respect of which theorem?
This Lipschitz retract.
Well, as I said, if you look at the first theorem, theorem A of Hajek, compact convex sets in any Banach space are uniform retracts, including in reflexive spaces. But if in a reflexive space you demand Lipschitz retractability of compact convex subsets, then it will force this space to be a Hilbert space. That happens in general Banach space, therefore in reflexive. So this situation is, I mean, these are two extremes. You know, you have arbitrary Banach space in theorem A, and you have Hilbert space in theorem B, and reflexive spaces, fall in the middle. And, well, I mean, yeah, the question could arise, yes. The question could arise, is it possible to realize compact convex sets in a reflexive space as slightly better than uniform retracts and worse than Lipschitz retracts? Well, I mean, you have to perhaps find the right analog between the two. There is something called, coarse continuous maps and stuff like that. An idea which arises in coarse geometry. But, so there are morphisms of different sorts. So you have to find the right candidate so that compact convex sets arise as P retractions, where P is an appropriate property that we have to. I think, yeah, that makes sense. Right. Are you able to see this entire screen? Because, oh my God.
Yes.
Yeah. So, here arises a problem. I mean, one of the problems is what you had raised. Yeah. I mean, could it be better in reflexive spaces? But there are a couple of more problems which naturally arise in the circle of ideas, which is to describe all Banach spaces such that the theorem of Ribe remains true for Lipschitz retracts in place of non-expansive retracts. I mean, theorem of Ribe, not of Hajek. Hajek concentrates on compact convex subsets. So Ribe's theorem is on closed convex sets. So Ribe says that closed convex sets are non-expansive retracts precisely when the space is isometric with a Hilbert space. So can you have a Lipschitz Lipschitz analog of Ribe? And then having already seen in Gödel's theorem that Lipschitz is a continuous retract of the ambient space, can you choose it to be a Lipschitz retract? So let's come to question B. It turns out that this property happens for all Banach spaces. So closed unit ball is always a Lipschitz retract of the ambient space, the big space. And you just have to consider these so-called radial maps. So which fix the elements inside the unit ball, and then you normalize it outside the unit ball and you get this map. But it's not, again, straightforward to show that it is a Lipschitz map. Okay, so it's a Lipschitz map with constant equals 2. And you can choose it to be 1. In other words, a non-expansive map if the space is a Hilbert space, right? The third line. And surprisingly, again, a result proved in 1970 by Karlovitz, and it is difficult to name. I have difficulty, pronouncing it. So it says that the previous property characterizes Hilbert spaces. X is isometrically Hilbert space precisely if R can be chosen to be non-expansive. So these are very satisfactory results and what it should be, but there are also surprises in store, and one of them is the following. Having already seen Brouwer's fixed point theorem and Goebbels' theorem, now this question makes sense. Do there exist infinite dimensional Banach spaces admitting a continuous retraction from the unit ball onto its square? It's again, there's a mistake. Admitting a Lipschitz retraction, because continuous retraction is always there in case of, as we learned in Goebbels' theorem. So can you choose it to be Lipschitz? So the third line from below, it should be Lipschitz retraction rather than continuous retraction. And the surprising answer was provided by Binyamini and Sternfeld in the 1980 or 81. So it says the following: in any infinite dimensional space, the unit sphere appears as a Lipschitz retract of the incidentally, this was listed as a crowning achievement of developments in function analysis that had happened in those 20 years, 60s and 70s by Lindenstrauss. So he had isolated it as a breakthrough result. So in other words, if you have an infinite dimensional Banach space, then you can choose Lipschitz mappings from unit ball to itself lacking fixed points. And so far as question B is concerned, question A here, this the Lipschitz analog of Reich's result. So Reich's result was about non-expansive mappings. So what about Lipschitz mappings? That means what about those mappings in which such that each closed convex set is a Lipschitz retract with a constant greater than 1. And this was proved last year, and it says that this happens exactly when the space is a Hilbert space, but isomorphically. So there is a difference. Reich's result says that it's isometric. The norm itself arises from an inner product, but here you have a norm which arises from an inner product, which is only equivalent to the given norm. And again, I mean, it doesn't follow from scaling constants here and there and getting this kind of a result. The techniques are entirely different. I mean, here the idea used, the idea that has been used involves what are called Banach limits and invariant means in this particular theorem. And this is what it is. And this follows from the next theorem. This follows as a corollary, the previous theorem, it follows from the next theorem. And it says that if you have a Banach space and a subspace Y, then I should add a little bit of, 1 minute background to this result. You see, recall, Tirsch's extension theorem. Continuous mappings or continuous functions taking values in the reals on a closed subspace can be extended to a continuous map on the whole space. And the question is, what about Lipschitz mappings? Can Lipschitz mappings be extended from subsets to or closed sets to the bigger spaces? The answer is yes. And that's an old result of McShane, E.J. McShane, which was proved in 1934, if I recollect it correctly, that given a metric space, then Lipschitz mappings on its subsets can be extended to the whole space. And therefore, LIP stands for Lipschitz mapping. So every Lipschitz mapping from Y to scalars can be extended to a Lipschitz map from X to the scalars. And there are one too many such extensions. The question is, can you make a suitable selection so that the resulting map is a bounded linear map, as I have mentioned here in the second line. So once, it's again a general theme. Like in the Hahn-Banach theorem, every continuous linear functional admits an extension, but how many extensions? Unlike in the Hilbert space case, there are infinitely many extensions. Can you pick up one suitable, appropriate extension that the resulting map that we define has some nice regularity properties? It's linear, it's bounded, or whatever. So if you can do that, that's what the two lines down there say, then it turns out that Y is nicely placed inside X. It's not really complemented, but it's locally complemented in a certain sense. I'm not going to go into the details because how much time do we have now? Yeah, I mean, can I take a couple of minutes?
Yeah, sure.
Okay, so once I have this kind of a situation, then Y is nicely placed inside X in the sense of being locally complemented. A notion which is slightly weaker, more general in other words, than being complemented. And the previous theorem follows from, as a corollary from this theorem. And these are, Lipschitz function spaces equipped with this natural norm. So LIP Y stands for all Lipschitz mappings from Y to R. And I require these functions to vanish at some distinguished point, let's say at the origin. Then under pointwise operations, it forms a Banach space when equipped with this norm. And one last thing before I close is the following. You see, in a Hilbert space, everybody knows about the projection theorem. So if you have a Hilbert space H and a closed subspace M, then you can complement this M by its orthogonal complement. So you can write H as M directs M per. And this M per is always closed. So using this decomposition, you can show that every closed subspace of a Hilbert space is linearly complemented by a norm 1 projection. So that's straightforward. That's a trivial exercise. And the natural question arose whether, what can you say about the converse? And this is again a very, very, very open, this was an open problem which was proved completely by Lindenstrauss and Zafiri in 1972, who showed that such Banach spaces are photocopies of Hilbert spaces. So they are exactly Hilbert spaces with a perturbation of the norm. So they are isomorphically Hilbert spaces. Once every closed subspace can be complemented by another space which is closed. So complement means they intersect in the origin only, and both spaces can be chosen to be closed. So, so the previous theorem gives a Lipschitz analog of the Lindenstrauss-Zafiri theorem. The previous theorem here, the last one over here. And this has a very nice consequence in terms of the Bartle-Graves theorem, which we encountered earlier, saying that if you have a surjective map acting between Banach spaces, then you can choose a right inverse, which is continuous and positively homogeneous. The question is, can you choose to be better than that, linear and continuous? And the answer is, again, available in this theorem, which follows from that main theorem in the previous slide. And it says that each closed subspace has this property. That means the corresponding quotient map has a right inverse, which can be chosen to be Lipschitz. And that happens again precisely when the space is a Banach, is a Hilbert space. So there are some questions which with which we conclude the paper, but then I can't be giving details of the questions that still hang fire right now. Okay, here I stop and I thank you very much for your attention, patience. Thank you.
Okay. Thank you, Professor Sofi. Any question or any comment?
Yes, I would like to make a comment here.
Okay.
Yes.
You have been talking about these retracts, absolute retracts, and neighborhood retracts, and so on. For these ideas are due to Al-Barsuk, and a very good book, Theory of Retracts, is very famous.
Who is the author, Professor Satyadev? Who is the author?
Barsuk.
Okay.
Barsuk.
Oh, is it an old book?
Old book, yes, very old book.
I see.
In topology, yes.
Okay.
It has lots of result about the theory of retracts and
in the topological setting, yeah.
Yeah.
So can you send me the details so that maybe it gives some?
I can, but actually that is from topology viewpoint of view. And
yeah, I know. Yeah, but then you always get some.
Yeah, but I want to tell you something more interesting than that. In fact, this is Spaniard. He wrote his thesis, and the title of that thesis was The Alexander Comology, and that actually appeared in Annals of Mathematics. So in that paper, he introduced Alexander Comology, but later on it became Alexander Spaniard Comology, and it's a very beautiful Comology theory. So one of the results, he gave an idea of what do you mean by saying that a subspace is totally embedded in a bigger space.
Mm-hmm.
See, if A is a subspace of B, when do you say that A is totally embedded, tightly embedded? Actually, he introduced the word tout, T-A-U-T, totally embedded.
Yeah, right.
Okay, then he proved a wonderful result that for Alexander Spaniard Comology, a closed subset of a compact Hausdorff space is totally embedded.
Okay.
That means closed subsets of the paracompact Hausdorff spaces, they are totally embedded. And actually, the definition was that you say that A is totally embedded in X, provided the cohomology of A is a direct limit of the cohomology of neighborhoods of A.
Okay.
That means the cohomology of A can be captured only by if you know the cohomology of the neighborhoods. Then you say it is totally embedded.
Right.
And he proved this wonderful result that a closed subset of a paracompact Hausdorff space is totally embedded. And he also proved a small result that a point subspace of any space is totally embedded.
Okay.
And as you know, point subspace are retracts.
Hmm.
Then I proved a result that actually arbitrary retract of any subspace, any space is totally embedded with respect to Alexander Spaniard Comology.
Of any topological space.
Any topological space.
Okay, okay.
Hausdorff, it has to be Hausdorff.
Right.
And this was my second paper of my PhD thesis, and Spaniard was very happy, and he gave another proof of this result, that a retract of a arbitrary Hausdorff space is always totally embedded. This simply means that retract is sitting very tightly there in the sense that its Alexander Spaniard Comology is simply the dark limit of the Alexander Spaniard Comology of all of its neighborhoods.
Professor Satyadev, I remember you had given a talk on this ages ago during the Ranchi conference of Indian Mathematical Society, and you had just returned from the US.
Could have been, yeah, could have been, yes.
Taught embeddings, it was, titled, if I
right,
remember it correctly. It was late 70s or early 80s.
Maybe, yeah.
Yeah, thanks for this information.
Yeah, from Comology, we find these retracts and absolute retracts also very important.
Yes.
And if you want to know its cohomology, forget it. Cohomology of its neighborhoods are enough.
Yeah, there are books, titled like, infinite dimensional topology. So it is the topology of infinite dimensional Banach spaces. So there are, I know at least 3 big volumes dedicated to this theme. Infinite dimensional topology. So the Polish school and the Dutch school had done a lot of work on it.
And actually, from this point of view, Alexander Spaniard Comology is very nice as compared to singular cohomology, because in singular cohomology, this is not true that even points are not totally embedded. Singular cohomology behaves very badly with respect to dimension, but the Alexander Spaniard Comology behaves very nicely with respect to dimension. So just I wanted to
thank you.
remark like this.
Yeah, Professor Satyadev.
Yes.
What is your definition of n retract?
N retract?
No, I think
There is a retract. There's a neighborhood retract.
Yeah, for Satyadev, it is a neighborhood retract.
Yeah, neighborhood retract means it is retract of a particular neighborhood.
Yeah. For Sofi,
Yeah.
Professor Sofi, what is your definition of n retract?
Oh, well, I haven't used that idea anywhere, and
No, you're using the words NR.
NR is non-expansive. You have a Lipschitz map with a constant k equal to 1.
Yeah, so the is that so these definitions are different.
So you choose that map to be nice enough. It's
I think there will be one needs some clarification that what the way Satyadev is using the word should be followed by what you are using.
Yeah, actually, this retract, absolute retract, NR, neighborhood retract, and absolute neighborhood retract.
Yeah. I know that terminology, and that's a standard terminology for topologists.
Yes.
But I think Professor Sofi is using
different context.
Different context, and probably Sofi's definition of NR followed by neighborhood retract or something. One has to check.
Yeah, actually, all I'm trying to say is that those sets, which we call retracts in different senses of the term, are arise as the images of mappings which are continuous, Lipschitz, non-expansive, or whatever. So it depends. I mean, I specify the conditions, the regularity conditions of the map, which is used to get a retraction.
No, sure. I just wanted to be clear about
Yeah, Professor Sofi.
Actually,
yes.
what he
Can
said.
you please stop sharing the screen, because Madam Khanduja needs to share the screen.
Okay.
You can continue the conversation.
Actually, Professor Sofi has been emphasizing continuous retract, and that is actually retract for us.
Yes. No, but I'm more importantly doing uniform retracts and other things.
Yes.
Okay, so thank you, Professor Sofi, for a very interesting talk. Thank you very much.